So to solve a second order linear homogeneous differential equation with constant coefficients, in any case, we write down the characteristic equation first, right? So and we try to solve the characteristic equation, and we have already covered the case of what happens if roots of the characteristic equation are two different real numbers, right? So it happens if and only if the discriminant of the characteristic equation is positive. Well, but we don't know yet what to do if the roots are complex, which happens when the discriminant is negative, or when the roots are equal, which happens when the discriminant is 0. So here is an example of a negative discriminant. So if the discriminant is negative, then the roots are complex. So they have a real part and an imaginary part. And as a matter of fact, the our formula, e to the power r1t and e to the power r2t, so they're still solutions, because when you substitute to the differential equations, nothing changes as compared to the previous week. So if you just substitute to the differential equation, you still get 0 equals 0. Yeah, but so the only problem is that the solutions are not real. So in order to extract the real solutions out of the complex solutions, we are going to use Euler's formula. So I hope that this is familiar. It's a very beautiful formula, right? So e to the power a plus bi, where a and b are real numbers, is expressed by this complex formula. And here is, let me go through an example, okay? But this example, it actually captures all the important features, so you can easily generalize this example to prove the theory. Anyway, so to solve this, first we write down the characteristic equation. So the characteristic equation is r squared plus 6r plus 25 is 0. So then let's find the discriminant. So the discriminant is 6 squared, 36, minus 4 times 25, so minus 100 is negative 64. So we have a negative discriminant, which means that the roots are complex. So the roots are minus 6 plus minus square root of the discriminant is 8i divided by 2. So this is minus 3 plus minus 4i. Right? So these are the two complex roots of the characteristic equation. So it means that, let's just take one of them, alright? So it means that the following function, y equals e to the power minus 3 plus 4i t, is a solution of this differential equation. But let me rewrite it according to Euler's formula. Right, so here, minus 3t is the real part, so this goes here, minus 3t, times 4i is the complex part, 4it is the complex part, so I will have cosine of 4t plus I sine of 4t. Right, so what we know is that if we substitute this whole thing as y into the differential equation, then we are going to get a true equality. But this is a complex number, so of course if a complex number equals 0, it means that its real part is 0 and its imaginary part is 0. So which means, essentially it means that the real part and the imaginary part of this, they are both solutions of the differential equation. So let me rewrite it with the real part, minus 3t cosine 4t plus I e to the minus 3t sine 4t. And so this is the real part, and this is the imaginary part, and both of them are actually a solution. So this is a solution of the differential equation, and this is a solution. Well, and you can probably guess that they are two linearly independent solutions, but let's just verify that they are indeed linearly independent. Okay. So let me find the Wronskian of these two solutions. So the Wronskian of so if say this is y1 and this is y2, then the Wronskian of y1 and y2 is the following determinant. The first row is e to the minus 3t cosine 4t and e to the minus 3t sine 4t. Right, so the second row is the derivatives of these two functions. So let me differentiate e to the minus, so minus 3 e to the minus 3t cosine 4t minus 4 e to the minus 3t sine 4t. So that's the derivative of y1. Now let me write the derivative of y2. So e to the still minus 3 e to the minus 3t sine 4t plus 4 e to the minus 3t cosine 4t. Okay? Alright, good. Now notice that we can actually take out e to the minus 3t out of the first column and again out of the second column. So then the whole thing is going to be e to the minus 3t squared, so e to the minus 6t times this determinant. Alright? And now let me find this determinant. So first we need to multiply like this. So this is minus 3 cosine 4t times sine 4t plus 4 cosine square 4t, and then in this order, right? But then we have minus and minus, it's going to give us plus, so this plus 3 cosine 4t sine 4t and plus 4 sine square t, which is cancelled together. Cosine square plus sine square is 4, so we just have 4 times e to the minus 6t. Yeah, because it was here, we took it out. And we see that the Wronskian is non-zero, hence y1 and y2 are linearly independent. So therefore the general solution of our differential equation is y equals c1 e to the minus 3t cosine 4t plus c2 e to the minus 3t sine 4t. But of course it is you can imagine that this works in the general case too, because I mean although we have gone through a particular example and there is no such thing as a proof by example, but if you try to go through the general theorem, then it's going to have all the same steps as this particular example, only with lambda and mu instead of 3 and 4. So let me just very quickly explain the steps of the proof, right? So steps. Sorry about this. Okay, steps of the proof. Right. So the first step is to realize that the function y equals e to the power lambda plus I mu t is in fact a solution. So this is a solution. The second step is to apply Euler's formula, right? To see that this is actually e to the power lambda t times cosine of mu t plus I e to the lambda t times sine of mu t. So which means that this is a solution and this is a solution. And the third step is to verify directly that the Wronskian of y1 and y2 is not 0. And you can guess that it's probably going to be something related to e to the lambda t. I'm not sure exactly, but